In this video, we are going to be drawing the complete mechanism of an E1 process. To start off, we're going to do a little comparison between SN1 and E1 reactions. The core steps are the steps that must be there in order for the reaction to occur. So the core steps for an SN1 reaction is the loss of a leaving group and then a nucleophilic attack. The core steps of an E1 reaction is the loss of a leaving group and then a proton transfer. For both of these reactions, there are more steps that can happen before and in between these core steps, but these are the ones that are absolutely necessary for the reaction to occur. So now we're going to look at some other steps that can happen, like I said before, in between. The bolded ones are the core steps that we just talked about, and then all of the other ones are other possibilities. So for both SN1 and E1, you can have a proton transfer at the beginning of the reaction. And this would be in a case where there was a leaving group that was not a great leaving group, like a hydroxyl group, and it needs to be protonated before it can leave. The second step is the loss of a leaving group, which is one of the core steps. And then in both cases, you can have a carbocation rearrangement. This is super important because you always want the carbocation to be as stable as possible. And then for SN1, you have a nucleophilic attack, and that's why you have that substitution. And then for the E1 reaction, you have a proton transfer, and that's where the base strips the molecule of its hydrogen. The hydrogen donates its electrons back to that sigma bond, and then that fills in the spot where that carbocation leaves open. And then for an SN1 reaction, you can also have a proton transfer at the end of the reaction. So now we're going to talk about cases where you would need that proton transfer at the beginning of an E1 reaction. So examples of this would be if you have a bad leaving group, and examples would be a hydroxyl group or an alkoxy group. And an alkoxy group is an oxygen connected to an alkyl group. So for example, OET is an alkoxy group. It is an oxygen connected to an ethyl. And these two right here are the exact same. It's just right here, it's written as OET, and then for this one, we actually drew out the two carbons. And then these two are just different examples with hydroxyls as the example. So now we're going to talk a little bit about carbocation rearrangement during an E1 process. So reminder, tertiary carbocations are the most stable. And here is an example of an E1 carbocation rearrangement. So the first thing that happens is the leaving group leaves, and it leaves that carbocation right here. But we see that we can do a methyl shift in this case. So if we move this methyl over to where this carbocation is, it puts that positive charge on a tertiary position, which is much more stable. And then in that case, you have your base, which in this case is water, which you know can either act as a base or an acid. In this case, it's acting as a base. It can strip that hydrogen off. The hydrogen donates its electrons back to the sigma bond, and it fills up the spot where the carbocation leaves open. And then you're left with your product. So practice, draw a detailed mechanism for the E1 reaction. So go ahead and pause the video, and just a reminder, hydroxyl groups are not good leaving groups, so you will need to protonate it to begin with. All right, so here is the very first step. Like I said, you need to do a proton transfer with a hydroxyl group. So remember, for E1 reactions, we use H2SO4, and the hydroxyl group right here goes ahead and grabs that proton to protonate itself. So now this is a good leaving group, which brings us to step 2. Step 2 is the loss of the leaving group, and make sure you're writing down the steps that you're doing. That's super important so that you can keep track of everything. The leaving group leaves, and then it leaves a carbocation right here. This would be a secondary carbocation, and then you have the loss of that water coming off. So in this case, you would also need a carbocation rearrangement. So if we were to move this methyl in a methyl shift, it would now leave that carbocation on a tertiary position, which is much more stable. The next step, let me move this over. The next step is that the water is acting as the base, and the water just comes from the acid over here. So the water takes off that hydrogen, the hydrogen donates its electrons back to the sigma bond and fills in this spot, and then you're left with the product. So how to get good at drawing out mechanisms, and this goes for any mechanism you draw, and it is simply to practice. There are a lot of different ways that mechanisms can be drawn, so it's just good to expose yourself to all different situations so that when you come across one on a test or a quiz, you're very comfortable and you know exactly what to do in every situation. I hope you found this video to be really helpful. The concepts and information presented in these videos will be true no matter what Organic Chemistry 1 class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.